Thank you for joining. This is at THS Mr. Jones with chapter 4.1, or sorry, 4.4. And this is the real zeros of a polynomial. Okay, this is really the main portion here of chapter 4. So our objective here is to factor and find zeros of a polynomial. We're going to use Descartes Rule, an intermediate value theorem and a couple other theorems to help assist with finding these real zeros. Okay, the first thing we have is the remainder theorem, and we talked about this a little bit, but if p of x, okay, and p of x is just some polynomial, is divided by x minus a. Okay, so this, when we did 4.3, remember this right here, I've got a 1 there, so that's important to note. So I can use synthetic division with this. But when my polynomial is divided by x minus a, then the remainder, which is r, is equal to p of a. Okay, so if I just take this a value and plug it into my polynomial, that will give me what the remainder is, and vice versa. So let's look at an example using that principle. Okay, so here's my polynomial, and I want to find p of 2. So we can do that a couple different ways. The first way most of us know how to do that is just to take 2 and plug it in. So if I want to find p of 2, we'll say 4, 2 to the 5th minus 3, 2 to the 4th plus 2, 2 to the 3rd minus 7, 2 squared plus 9 times 2 minus 5. Okay, and hopefully we can just plug all that into the calculator. So I got 4, 2 to the 5th minus 3, 2 to the 4th plus 2 to the 3rd minus 7, 2 squared plus 9 times 2 minus 5. Enter, and I will get out 81. Okay, so that's the way we've been doing it. Okay, but the rational root theorem says if I take my polynomial and divide it by x minus a, then then my remainder is the same thing as p of a. So this should be my remainder. So if I take this polynomial and divide it by 2, okay, which would have been x minus 2. Okay, x minus 2 would have been this part right here. Okay, and then I put in my coefficients. So I got 5, 4, 3, 2, 1, 0. So now I don't have to put in that placeholder. Okay, and what I'm looking for is this number right here. I'm wanting that to be 81. Okay, so I will bring down my 4. I will multiply. I will add. I will multiply. I will add straight down. I will take 2 times 12, get 24. I will add down, get 17. I will multiply and get 34. I'll add and get 43. Multiply 2 times 43 and get 86. Add to get 81. So we notice here that 81 here is the same as 81. Okay, so, and notice a lot of times we can do all of this stuff without putting this long string into the graphing calculator. Okay, so your remainder is your value evaluated. Okay, so we've got what's called the factor theorem. If p of a equals 0, okay, so if I would have plugged 2 in, okay, and if I would have got 0 out, then x minus a is a factor of p of x, of your polynomial. Conversely, if x minus a is a factor, then when I plug it in, I get a 0. Okay, so tell if x plus 2 is a factor of this polynomial. Well, what I want to do is I want to check, is p of negative 2 0? That's my question. So we'll take synthetic division and we'll pull out a -2 is what we're dividing by. Remember, we set that equal to 0 and solve it. So I got 3, 2, 1, 0. So I don't need any placeholders. And we're curious about that remainder there. Okay, so I bring down the 1, take -2 times 1, I get -2. I'm going to add those together, I'll get -4. I'll multiply those together and get 8. I'll add and get 3, multiply, get -6, add, I get 0. So that's great, okay? This, when your remainder is 0, that tells us that this is a factor. So when I factor that out, when I pull out x plus 2, what do I have left? Well, this is my remainder, this is my constant, that gets x, and this gets x squared. So I will write x plus 2, which is what I divided by, x squared minus 4x plus 3. Okay, now let's look and see if we can factor this. Factors of 3 that add to 4. So I've got x plus 1, x, factors of 3 that add to 4, that's 3 and 1. Signs are the same and they're both minus. So this is the same as p of x. So we are completely factored out. Okay, and we can kind of check this. Okay, these are zeros. So if I set each one of these equal to 0, I get x equals -2, 3, and 1. So if I go to graph that here on the graphing calculator, I get x to the third minus 2x squared minus 5x plus 6. Oh, I need to zoom standard here. Okay, well, notice it crosses at -2, it crosses at 1, it crosses at 3. We can also check the table out. If I plug in -2, I get a 0. If I plug in 3, I get a 0. And if I plug in 1, I get a 0. Why do I get a 0? Because they are all factors of that polynomial. They give me a 0 in synthetic division. Are x minus 3 and x plus 2 factors of this polynomial? Okay, so we'll first, it doesn't matter which one you check first. Okay, so let's check this one. So I'm going to bring a +3 for my synthetic division. I've got a 1. I don't have an x to the third, so I put a 0. Minus 13, 0, and 36. So I've got x to the fourth, 3, 2, 1, constant. And we're looking at this remainder here. All right, so we'll bring down the 1. We'll multiply 3 times 1 and get 3. We'll add straight down. We'll multiply, get 9. We will add and get -4. We will multiply and get -12. Add to -12. We will multiply to get -36, and we get 0. Okay, so what is left? So this was my remainder. That is my constant. I get x squared, x to the third. Okay, so I'm gonna come down here and I'm gonna rewrite it. So this, or let's just go over here. This was what I had. So then I had x minus 3 is a factor. Why is it a factor? Because I got 0 here for my remainder. Okay. Now I want to check if x plus 2 is a factor. Well, if x plus 2 is a factor of this, then it must also be a factor of this down here. Okay, that's important to know, because now I don't have to rewrite it and do all these. So I'll just continue with this one, and I will put a -2 out front. Okay, I'll bring my 1 straight down, multiply, get -2, add, I get 1, multiply, I get -2, add, I get -6, multiply, I get 12, add, I get 0. So is x plus 2 a factor? Yes, because when I plugged it in or did the synthetic division with -2, I got 0. So I also have x plus 2 as a factor. So this is constant x squared. Well, this is what I have. I have x squared plus x minus 6. Factors of 6 that subtract to 1. 3 and 2, x, signs are different, the bigger one is positive. So I have x minus 2, x plus 3. And that's what I got, okay? This whole thing factors out into those 4 factors. Notice that matches with how many factors I have. Again, can we check this? So I have x, let's clear that out, x to the 4th minus 13x squared plus 36. Graph. Okay, notice it crosses my x-axis at 1, 2, 3, 4 times. Okay, so if I were to set each one of these equal to 0, I would have got 3, which matches with this over here, minus 2, which matches with this over here, 2, which matches with this one, and minus 3. Well, looky here. Minus 3, minus 2, 2, and 3. Again, check it on the table. I got 3, 0. Negative 3, 0. Negative 2, 0. 2, 0. That tells me that they are indeed, that tells me indeed that they are all zeros. Okay? Calculator is a great resource for checking your answers on this kind of stuff. Okay, so searching for zeros. Okay, not every time are they going to be so easy to find. So we have to talk about searching for zeros, and this is where things get a little more difficult. A polynomial function cannot have more real zeros or zeros than its degree. So if I have an x to the 4th, we've talked about this, I'm looking for 4 answers. Okay, it cannot have any more than 4 answers. So I'm looking for 4 zeros for that. All right, we have what's called the rational root or the rational zero theorem. Okay, if this is my polynomial, okay, I've got some string of terms out there, then all my rational zeros, okay, are in the form of, so rational zeros equal plus minus factors of a0 over factors of an. Okay, we often call this P's and Q's. Okay. So we'll plus minus P's over Q's. Okay, I call this out here your P, this over here your Q. Okay. Doesn't really matter. Just know that it's factors of your last one over factors of your first one. And it's all the positive and negative ones of that. So determine the possible rational zeros of this polynomial and test them. Okay? All right, so all my my zeros, so my P's and Q's, okay? So I do factors of this last number, okay, which is 6. So that is 1, 2, 3, and 6. Over factors of your first one, so the last one and then first one, which is 1, so which is just 1. Okay. Now we do all the combinations of these and these, positive and negative. Okay. So I have a plus minus 1 over 1, plus minus 2 over 1, plus minus 3 over 1, plus minus 6 over 1. Okay, and those are my possibilities. Okay, a lot of times we'll have numbers down here and we just got to keep going. Okay, I'll show you some examples of that. So how do I test them? Okay, well, all I got to do is do the synthetic division with them. So we'll test 1. In my polynomial, I got 1 minus 1. I got 4, 3, 2, 1, 0. Okay, don't need a placeholder. So 1 minus 5 minus 1 minus 6. Okay, so I bring down the 1, multiply, add, multiply, add, multiply, add, multiply, add. Okay, so 1 is not a 0 because I did not get this number. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8 items, okay, that I'll need to check. So what if I do -1? Okay, now sometimes we can just go in here and, like, I might change that to a -1 and redo it all. So I bring down a 1, I multiply, I get -1. Add, I get -2. Multiply, I get 2. Add, I get -3. Multiply, I get 3. Add, I get 2. Multiply, get -2. Add, you get -8. So that one didn't work. Okay. Some of you might just say, well, can't I just plug this in? Okay. If I take 2 and plug it into this, so 2 to the 4th minus 2 to the 3rd minus 5, 2 squared minus 2 minus 6, can I just plug all that into the calculator? Yep. And you're going to get -20 in that case. So 2 is not a 0. If you plug in -2, so you get -2, 4 minus -2 to the 3rd minus 5, -2 squared minus -2 minus 6. Okay, you have to be careful this way because of all these parentheses in the negative sign. In this case, you get 0. Okay, so is -2 a 0? Yes. So we might, I don't know, just note here that x equals -2. So x plus 2 is a factor. Okay, so we just had, okay, so we checked all those, now we need to check those. Okay, this can get really long. Okay, so we can shortcut this just a little bit. So if I would have plugged in -2 with synthetic division, okay, so -2, that's 1, -1, -5, -1, -6, I get 1, -2, -3, 6, 1, -2, -3, 6, 0. Okay, I can redo the rational root theorem for this. Because now my new polynomial is this: x to the 3rd minus 3x squared plus x minus 3. So I take factors of this one, which are 1 and 3, over factors of this one, which are 1. So now I'm only looking at plus minus 1 and plus minus 3. Well, we checked plus minus 1, and it didn't work. Okay? If it would have worked for this one, it would have worked for the one before. So now all I need to do is check positive, -3. So if I check 3, okay, I get 1 minus 3, 1 minus 3. So I get 1, 3, 0, 0, 1, 3, 0. So I get constant x squared. So I get x squared plus 1. X equaled 3, so x minus 3 was a factor. So I get x plus 2 was a factor, x minus 3 was a factor. Now you might be thinking, well, can't I do more with this one right here? Well, think about that. If I take x squared plus 1 equal to 0, I'll subtract 1, minus 1. X squared equals minus 1. If I take the square root, I got a negative under there, so I got an I. So this is what we'll end up with. Okay? So that was a lot for that one problem. Okay? All we really wanted were to determine the possible. So this was determine the possible solutions, or possible zeros. Okay? Again, you can graph it and check it on the graphing calculator. Okay, so write as a product of factors. All right, in order to do this, we first want to determine our factors, or our possible roots. So we'll do P's and Q's. Okay, this is P, so 45. So I need factors of 45. So that's plus minus 1, plus minus 3, plus minus 5, plus minus 9, plus minus 15, plus minus 45. All over 1. Plus minus 1. Okay, which I really don't need that because they're the same. Okay, they won't change. So now we just need to evaluate all of these zeros. Okay, well, maybe a little bit quicker way, if we've got access to this graphing calculator here. So I've got x to the fourth minus 4x to the third plus 4x squared minus 36x minus 45. If I go to the table, can't I just check them on here? Okay, so we'll plug in 1. Well, I got negative 80, so that's not a 0. Plug in minus 1. Oh, I got 0. So x equals minus 1. That's one of them. Okay, and we can just keep going through. How about 5? Oh, 5 was 1. Negative 5? Nope. So I checked those. Forgot 3s. 3. Negative 3. So those two don't work. 9. Nope. Negative 9. Nope. 15. Negative 15. Nope. 45. Negative 45. Nope. Okay. So it looks like the only ones that are working are 1 and 5. So if I take and do the synthetic division with that, so I've got 4, 3, 2, 1 constant. So 1 minus 4, 4, negative 36, negative 45. I should get 0 as my remainder. So this is just kind of double checking. So I've got 1 minus 5, 5, 9, negative 9, minus 45, 45, 0. Okay? Do it again, this time with 5. So I got 1, 5, 0, 0, 9, 45. I get 0. Okay? So the question said write it as a product of factors. So since negative 1 was a 0, x plus 1 is a factor. Since 5 was a 0, x minus 5 is a factor. Now when I factor those out, I get this left. So constant x squared. You get x squared plus 9. Okay, which that's my answer because I'll get imaginary zeros here, and we'll talk about that later on down the road. Now we can narrow our zeros down a little bit more. So we have what's called the Descartes Rule of signs. Okay, and in my polynomial where the constant is not 0, okay, the number of positive real zeros is equal to the number of sign changes in P of x or less by an even number. Okay, so if I look through my polynomial and I see that there are let's say there's 6 sign changes. So that means there's 6, 4, 2, or 0 positive real zeros. Okay. The number of negative real zeros is equal to the number of sign changes in P of minus x or less by an even number. Same thing. If I get, let's say I get 7, that's 7, 5, 3, or 1. Okay, so there's at least 1 in there. Okay, now this can be helpful. Sometimes if you're just, shooting in the dark and you're not sure where to start, sign changes is one place we can look at. So determine the possible combinations of zeros. Okay, so we've talked about the total number of zeros, and we've talked about positive and negative, and we've talked actually about imaginary just a little bit. So what I want us to do, and this is a little bit different than the book, is I want to find the positive, negative, imaginary, and total chart. Okay, so I've got a chart for this that I'll show you. All right, so if we look at the total number of positive, okay, so total number of positive will be the number of sign changes in the original polynomial. Okay, so I've got, this is plus, minus, minus, plus. So the signs change 1, 2 times. So it changes here and it changes here. It's the same between those two terms. So that's 1, 2. So number, if we do plus, minus, I, total. Okay, so that's 2. But remember, I can have fewer by an even number. So I can either have 2 or 0. All right. If we look at negative zeros, all right, we look at negative x, f of negative x. So I plug it in. Okay, and I figure it out. Well, negative x to the third is minus x to the third. Negative x squared is a positive x, so that one stays negative. So negative x times negative 5 is a plus 5x, and I still have a plus 6. So this is negative, negative, positive, positive. So that changes once. Okay, so there has to be one negative 0. Okay, so I come over here, and if I have 2 positive, I have to have 1 negative. If I have 0 positive, I have to have 1 negative. I have to have 1, because if I subtract 2 from that, I get a negative 1. I don't want that. So there's at least one, or there is one negative 0. Okay. Well, if we remember from up here, I had a 3 was my degree. That tells me that there's a total number of 3. So if there are 2 positive and 1 negative, there have to be 0 imaginary for a total of 3. 2 plus 1 is 3. But I could also have 0 positive, 1 negative, but I still have a total of 3, so my other 2 have to come from the imaginary side. Okay, and this is the plus minus IT chart that we will be filling out on most of these problems to kind of help us out. Okay, so you need to know how to do that. Determine the possible combinations of zeros in this one. Okay, so again, we look at sign changes of P of x. So P of x was plus, minus, plus, plus, minus. So that's 1, 2, 3 sign changes. Okay, so positive zeros was 3 or 1. If I look at P of minus x for the negative, okay, so I have negative x to the 4th, minus 2 negative x to the 3rd, plus negative x squared, plus 2 minus x, minus 2. So this one is positive. This will stay negative, so make that positive. This will be positive. This will be negative. This will stay negative. So I've got plus, 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 minus, minus. So I only have one sign change. So for negative is 1. But I have a total of 4. So I do plus, minus, I total. Okay, so then we look at our combinations here. Okay, so I could have 3 positive, 1 negative for a total of 4. So I can't have any there. I could have 1 positive, 1 negative, still have a total of 4, so that means 2 have to come from there. And that's all my combinations. Okay. Sometimes you'll have maybe 4, 5, or 6 there. Okay, that won't always be a 1. All right, so here we go, kind of into some harder problems here. So we're going to write x to the 5th plus 2x to the 4th minus x minus 2 as a product of factors. Okay, so let's first, so step 1 is our plus minus I t table. Okay, that's what we want to look at first. So we need to find the sign changes. So looking at p of x, okay, so p of x is plus, plus, minus, minus. So I have one sign change, which means that there will be one positive. I don't need to put in the x to the 3rd or x squared in this. So if I look at p of minus x, some of you might be noticing that if I put in a minus x here, since it's odd, it will stay a negative, or it'll change a sign in the front. So this one, since it's even, will stay the same sign. Since this one is odd, it will change signs. And since this one doesn't have an x, it will stay the same. Okay, so that was minus, plus, plus, minus. So that's 1, 2 sign changes. So I have 2 or 0 negative. So if I do my plus, minus, I total, my total has to be 5. Okay, so I can go ahead and fill that one in first. So 5. So I could have 1 positive or 2 negative, which that only gives me 3. So then 2 have to come from the imaginary. Or I can have 1 positive, 0 negative, still have a total of 5. I need 4 from that one right now. And again, we are not really worried about that column just yet. Okay. All right, so now we will look at our P's and Q's. Okay, so P is this last one. So I need factors of 2, so that's 1 and 2. And our Q is this 1, so 1. So my possible rational zeros are plus minus 1, plus minus 2. Well, that's pretty nice, okay? Because I only have 4 to choose from. Okay. Now, I need 1 positive and 2 or 0 negative. Okay, so let's just check. Let's check 1. Okay, so I get 1, 2, 0 for x third, 0 for x squared, minus 1, minus 2. Okay, so 1, 1, 3, 3, 3, 3, 3, 3, 2, 2, 0. Good. So we found our positive one. So x equals 1. Now look here. This chart told me I only wanted 1 positive. So since I found my 1 positive, I'm not even going to check positive 2. I know it won't work. Okay. So I'm going to continue from here, and I will check minus 1. Okay. So I've got 1, minus 1, 2, minus 2, 1, minus 1, 2, minus 2, 0. Okay, so x equaled -1. Now think about it. I either wanted 2 negatives or no negatives. Okay, well, since -1 worked, guess what also is going to have to work? -2 will also work. But because I want all the factors, I still need to divide this by this -2. So I got 1 minus 2, 0, 0, 1 minus 2, 0. So x equaled -2, which means that here x minus 1 is a factor, x plus 1 is a factor, x plus 2 is a factor, and what am I left with? Constant x squared. So x squared plus 1. So then I get x minus 1, x plus 1, x plus 2. Okay, and again, I can't do anything with that because that's an imaginary root. So notice, 5. Total of 5 zeros. I had 1, 2, 3, 4, 5 coming from this. So I will have 1 positive, 2 negative, 2 imaginary for a total of 5. Okay. This is really what we're getting into. This is a great problem to maybe star this one. We should have starred that one. Okay, that's a good one right there. Upper lower bound rules. This is help. A lot of people forget this, but this is super helpful in narrowing down what numbers you're going to pick for your synthetic division. Okay, so if f of x has a positive leading coefficient and is divided by x minus c using synthetic division, so I bring c out front. Okay, if c is bigger than 0 and the bottom row is 0 or positive numbers, then c is an upper bound. Okay. What do I mean by that? Okay. I mean that c is higher than what my 0 should be. So if this happens, if c is bigger than 0, I need to get down to a lower number. Okay, that's what it means. If c is less than 0 and the bottom row alternates between positive and negative, and I note here that 0 can either be positive or negative, whichever one you want. Okay, then c is a lower bound of f. So then I need to pick a c higher. Okay. So remember on our calculator, if we go to find a 0, okay, if we look for some of these zeros, let's say I want to look for that 0. Okay, I hit second calculate 0, right? And it asks me for a left and right bound. That's very similar to this upper and lower bound. Okay, except here on left and right bound, it wants to the left, pick an x to the left, pick an x to the right. Okay, upper and lower would be pick one above and pick one below. Okay, and I think Casio calculators might ask for upper and lower bounds instead. Okay, but they're very, very similar. So let's look here. Find the real zeros of that polynomial. So we want to look at the sign changes. So step 1, we look at f of x sign changes. So it was plus, minus, plus, minus. So that was 1, 2, 3 sign changes, right? So I'm going to have, so positive zeros will be 3 or 1. F of negative x, Okay, so that's odd. So this one changes to minus 4x to the third. That one stays the same. This one changes. That's 36x. And this one stays the same. So it's minus, 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 minus. So negative zeros is 0. I don't have any. Okay, there's no sign changes. Okay, so if I do my chart, I got a total of 3. Okay, so I've got my plus, minus, I, t. Total of 3. So 3 can be positive, meaning 0 have to be here and 0 have to be there because I got a total of 3. I can have 1 here, 0 here because we said I can't have any negative. Okay, so 2 have to come here for a total of 3. Again, we're ignoring this for right now. Step 2 is our P's and Q's. Okay. Now, here I don't want any negatives, so I'm not going to do the plus minus. I'm just going to do the positive. So I want factors of 9, so that's 1, 3, and 9, over factors of 4. That's 1, 2, and 4. Okay, so I've got 1 over 1, 3 over 1, 9 over 1, then I come back here. So I got 1 over 2. I got 1 over 4. Okay. Let's 3 over 2 and 9 over 2. Then we move to 4. So I have 1 over 4, 3 over 4, and 9 over 4. Anyway, you just got to get all the combinations of matching these numbers up. Okay. So now we are going to test them. Okay. So let's test with positive 1. Okay, so we have 4 minus 1, 36 minus 9. Okay, so when I do this, I get 4, 4, 3, 3, 39, 39, and 30. Okay, so since f of x here has a positive leading coefficient, okay, so this has a positive leading coefficient, and c is bigger than 0, and all of these are positive numbers, and they're all positive, then c is an upper bound, okay? That means that I need to pick a number less than 1 and try it for a 0. Okay, so if I go through here and pick a number less than 1, we will try that. Okay. We could also maybe look on the calculator to see what we get. So we could, so instead of trying 1, so that didn't work, I might try a half. Okay, that's less than 1. This is bigger than 1, bigger than 1, less than 1, less than 1, less than 1. Okay, so if I try half, okay, so I get 4 minus 1, 36 minus 9. So I get 4, 2, 1, a half, 36 plus a half is 73 over 2 times a half is 73 over 4. If I add that, I get 37 over 4. Okay. Well, again, this was leading coefficient was positive. This was bigger than 0, and all these are positive. So I still need a number less than a half. Okay, so I'm not going to check these other numbers. So this is not less than a half. So I'm not going to check it. So I'm going to check 1/4. So I get 4 minus 1, 36 minus 9. Okay, so I get 4, 1, 0, 0, 36, 9, 0. Okay. Now what's left? Well, this is constant x squared. So I had x minus a fourth from this one. Okay. And then I had x squared, 4x squared plus 36. Okay. Which here, this has to be a subtraction for me to get answers from that. Okay. So this is actually the only real zero I have. So in this case, it falls under this line. 1 positive, 2 imaginary for a total of 3. Okay. We can also, instead of writing it this way, we can write 4x minus 1. Okay. Which I like this 4x minus 1 a lot better. All right, so we have the intermediate value theorem we talked a little bit about. Okay, and if I have some graph here, okay, and it says A and B are real numbers and A is less than B. So let's say that this is A and this over here is B. This is B. If f of A and f of B have different signs, which they do, okay, so right here is f of A, and up here is f of B. Have different signs, then there's at least 1 0 between them. And right here is my 0. Okay. Now the reason I use this, or the reason we really talk about this, is for the bisection method. Okay. So if I have opposite signs, okay, I'm going to find the x between A and B. Okay. How do I find that? We'll call this point C. I'm going to take C equals A plus B divided by 2. Okay? So you're going to find the x between A and B and retest using synthetic division and intermediate value theorem. So now I'm going to see, is it between this gap, or is it between this gap, or is C the 0? Okay? C might be right here, right next to it. Okay, so then these will have the same sign and these will have opposite signs. Okay, and that's what we're going to look at here next. So approximate the 0 of that function right there. So if we just quickly look here on the graphing calculator, x to the 5th minus x to the 4th minus 1. If we graph that right here, okay, I can look right here, and here's 0 and here's 2. I know that my 0 is somewhere between 0 and 2. Okay, if we look at the calculator here, if I plug in 0, I get minus 1. If I plug in 2, I get 15. Okay. Thus, it is somewhere between those two numbers. Okay, so what we do here is, if I graph this out here, I've got 0 and I've got 2. And my number is somewhere between those two. Okay, so I'm going to cut this in half, which is 1, and I'm going to see where that is. So at 2, we were positive. Here, we were negative. Okay, if I plug in minus 1, okay, if I plug in minus 1, I get negative 3. So here, we're at negative. So that tells me, okay, since these two were the same, that means my graph is somewhere down here between those two numbers. Here and here has different signs. So that tells me my graph falls somewhere between those. So we're going to take the distance between 1 and 2, and we will split that in half. So we get 1.5, or 3 over 2. Okay. If I plug in 3 over 2, so I'll just f of 3 over 2, I get some positive number. So this one is positive. Okay, so that means my graph is here to here. So my 0 is somewhere between 1, and 1.5. So if I find the distance between here and here, okay, that's 1 plus 3 over 2 divided by 2, which is 1.25 or 5/4. Okay, so if I plug in 5/4, I get a negative number. So this one's negative. So then, okay, so we marked out this section, we marked out this section, okay? So now since this was negative, here and here's negative, so we mark out this section, so it's got to be somewhere in between here. Now this can continue forever. Okay? Unless your midpoint or your bisection lands on the 0, this will keep repeating for several times. Okay, so let's just do it one more time. And we'll just change these to decimals. This is 1.25, and this was 1.5. So we're going to go between 1.25 and 1.5. So if I take 1.25 plus 1.5 divided by 2. That's 1.375. And if I plug that in, okay, if I go to my table and I plug 1.375, if I plug that in, I get a positive number. So this one, we split this in half, and we get a positive number. So that marks that section out. So I know that my 0 here is between 1.25 and 1.375. So just one more guess, we know it might be right in the middle of it. So we would estimate that my 0 is 1.3125. That's my estimation. Okay. Now, can we find a more exact? Sure. If I go to my graph and I hit second calculate 0. Okay. If I go to the left bound, so this is to the left. If I go to the right, so that's to the right, it tells me that the x is 1.324. Okay. 1.31. Pretty close. Okay. I'm a little bit far off, but guess what? I can keep going further and further and further and further and further. I can get within, 1/1,000,000th, 1/1,000,000th place value of getting that exact answer. Okay, but this is why we look at intermediate value theorem. Okay, in computers, this is what your calculator is doing when we put left and right. When I put the left one in, it gives me this one. When I put the right in, it gives me B, and it's running this program in your calculator. Okay, so graph the function. Okay, so we want to graph this function. So we first want to find the y-intercept. Okay, that's plugging in 0 for x. So I get 0, comma, well that's 0, that's 0, that's 0, that's 0, negative 22. Now we want to find the x-intercepts, or my zeros. That's what this whole 4.4 is about. Okay, so we want to look at our sign changes. So f of x, that's plus, minus, plus, plus, minus. Okay, so that's 1, 2, 3. So positive zeros are 3 or 1. If I look at, this is h of x, so that doesn't change with a negative x, so that's 2x to the 4th. This one changes, so that's plus 2x to the 3rd. This one doesn't change. This one does change, and this one doesn't change. So that's plus, 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 minus, minus. So that's one sign change. So negative zeros is 1. So if I do plus, minus, I, t, I get a total of 4. So there's 4. I can have 3, 1 negative, so that's already 4, so I'll have 0 there. I can have 1 positive, 1 negative, 2 I, for a total of 4. And that's all the combinations I can do. So we're either looking for 3 positive or 1 positive, and I'm just looking for 1 negative. So then we go to P's and Q's. So that's factors of 22. So let's see, factors of 22. That's 1, 2, 11, 22. And factors of 2, 1 and 2. And again, I want plus minus. So we got plus minus 1 over 1, plus minus 2 over 1, plus minus 11 over 1, plus minus 22 over 1. Then we got plus minus 1 over 2, plus minus 2 over 2 is 1, so I don't need to put that again. So plus minus 11 over 2, and plus minus 22 over 2, which is 11. So these are my possible zeros. So now the long process is just testing your zeros. Okay? And that's what we use synthetic division for. Okay? That's what we use the upper and lower bound rule for. Okay? That's what, and it's going to be a long process, and I want to see that work. Okay? So we can, I'm just going to speed this process up just a little bit. Okay? We'll test, let's test 1. I'll show you one example of synthetic division. 5, 17, negative 22. Okay, so 2, 2, 0, 0, 5, 5, 22, 22, 0. Okay, so this was a 0. So x equals 1. It crosses my x-axis at a 1. Okay, and notice here that since my leading coefficient was positive, this was bigger than 1, and all of these are positive, then it is an upper bound. So that tells us, okay, that there will be 1 negative. Okay. So now we just need to test negative numbers. Okay. So if I come here, okay, I can ignore all the positives now and just go straight to the negatives. Okay. So if I can kind of speed this up by plugging them in. And looking at the table. If I plug in negative 1, I get minus 30. Negative 2, I get minus 12. Negative 11, I get that. Negative 22, I get a big positive number. Negative 0.5, negative 11 over 2. None of those give me a 0, which tells me, okay, that I will have to estimate that value. Okay, so if we kind of start graphing here, I'm at 0 minus 22. That's minus 22. I cross it, x equals 1, and I'm crossing somewhere over here. Okay, I will have to estimate that value. Okay, and that's where we use the bisection method. That value is somewhere between negative 1 and negative 2. Okay, because this was positive and that was negative. Okay, if I go down to negative 1/2, okay, I don't need that because I'm looking between negative 1 and negative 2, so I'd have to bisect that just a little bit. If we calculate that 0, okay, this is what our graph looks like. Here's 1. That's down to minus 22. Okay. I want to go to the left side of that 0. There I'm on the left. There I'm on the right. So that x, negative 1.85. So there's minus 1, minus 2. There's that 0. Okay. Now, what's the end behavior like on this? Well, this leading coefficient here was positive, and I'm x to the fourth. So that means I'm going to open up. That shouldn't be a v, but I've got x to the fourth should open up, right? And again, remember, I don't have to have all those humps. So if I kind of rearrange this window here, okay, we'll say there, we'll go lower on my minimum. Let's say we go to negative 30. Okay, we still can't see that bottom portion right there, so let's change it some more. Let's go minus 5 on the x, 5 on the x. Let's go minus 50 there. And let's go 50 there. Okay, so that kind of shows what my x to the fourth looks like. So I'll just kind of sketch that out. Remember, I need some points on here. And I could also find some extra points in here. Maybe I plug in minus 1 on the table. I plug in minus 1, I'm at minus 30, so I'm way down here. Maybe I plug in 2 here, and I'm at 48. Okay, check your graph. I'll be something like this. Okay, I want to see some points on your graph. Okay, I'm totally fine with you using your calculator to kind of help you out and check some of your answers, but I want to be seeing this table. I want to see some synthetic division, all that kind of stuff. Okay, so here's your suggested problems on page 432. I want you to do 81 through 84. Those are just some simple true-false questions. Okay, give those a try. They're good questions that I can put on the test. Thank you for tuning in. As always, this is @THS Mr. Jones signing off.